Hello everybody, this is Alessandro Laurenza from Midas IT Europe. Today's webinar I would like to present a three-span steel composite top girder bridge analysis and design with Midas Civil. We will take a look quickly at the bridge. We will perform the model in the second stage of the presentation through the wizard built-in Midas Civil. We will perform the analysis inside the model, create some load combination, checking some results, and performing some ULS check required for composite girder design. The key aspect of a composite tub girder, as the name of such a girder tells, is they have a tub shape in a pre-composite stage composed by a bottom flange, two webs inclined typically, and two top flanges. The section is closed by a concrete deck on the top, and added shear studs are installed to absorb the longitudinal shear. In the pre-composite stage, the section is open, and the pseudo box shape is reached thanks to the top lateral bracing as shown in this picture. Tub girders are sometimes selected over eye girders for several reasons. The most important one is engineering reason, and design motivation is the large torsional stiffness, 1,000 times larger than a comparable eye section, and which make those kind of bridge ideal for carved interchanges. This increased torsional resistance reduce the relatively large deflection of the girder on the outside of the curve. They are selected also for other reasons like aesthetic, thanks to the pleasing and smooth appearance they offer. Potentially, they are also more economical for long span application because theoretically, due to the increased bending strength offered by the wide bottom flange, less quantity of steel is required. And one of the most important aspects is also the maintenance and durability of a composite tub girder bridge, because they are easy to inspect. In fact, normally the minimum height is 120, 140 meters, so easy to inspect for a human being. They remain most of the time dry. They are less susceptible to the corrosion since low chance for debris to accumulate and then interior environment remain all the time protected. The scope of this webinar will be to show the capabilities of Midas Civil, especially during the modeling and the design phase. The focus will be on the main Turber main composite girders, as they will be modeled as simple line beam elements. The deck as well will be modeled as a composite, as frame elements. The design of internal external bracing, stiffness, diaphragm, and piers are not included in this webinar, and all the consideration comply with the Eurocodes, in particular Eurocodes 3, Eurocodes 4. The bridge is a roadway bridge, 3-span, 48, 64, 48 meter. The deck width is 12 meter, where the edge barriers occupy 50 centimeter at the ends of the deck. The bridge is carved for this particular example that I've created, I utilize not a hard curvature, so I use a radius of 500 meter. Number of two main girders will be used as shown in the previous typical cross-section. Construction stage analysis will be performed in the way that the concrete deck parts over interior supports will be cast after the parts on the central midspan and the outer supports. So basically, we will cast the parts of the deck over the negative moment area in later in order to reduce the minimum the crack. Time-dependent material properties will be used in this model, especially for shrinkage, and a concrete compressive strength curve will be used for the deck. Traffic load analysis as well will be performed with the LM1 load model 1 of Eurocodes. Instead, the properties of the steel components will be S355, concrete C3545 for the concrete deck, C3037 for the piers and columns. Reinforcement steel will have a grade B500B. In this slide, I show the cross-section geometry for the main girder, especially section 1 will be used for the span 1, 3 and the positive moment zone of such spans. Section 2 will be used for the negative moment zone of span 1, 3 and for the total span 2. The total height of the webs in both sections is 1.95 meter. The total width of the bottom flange is the same, 2.1 meter. The main difference between the two sections is the bottom and top flanges thickness. Diaphragm will be modeled in Midas Civil in forms of a steel I-beam. So a plate, basically what is done in the practice. Plate diaphragm are used with the consolidated reinforced by two plates, so to create a I-beam. This I-beam will have the same height of the main girders. Diaphragm will be modeled only over the supports. The top lateral bracing will be still T-shaped with this kind of UKB profile. This will not be modeled, as I will tell later. It will be, it's just mentioned because we need to know the area of the top lateral bracing components. Intermediate supports will have this shape. The column is represented by a solid circular column with radius 2.5 meter and height of 7.5 meter. Total length of the pier cap it's 9 meter. It's formed by two tapered sections, 3 meter long at the ends. The central section as well is 3 meter. This straight. Maximum height is 3 meter, minimum is 1.5 meter, and the depth of the pier cap is 3 meter as well. The construction stage are shown in this lab. Construction stage 1, supports, columns, and piers are installed. Construction stage 2, also steel top girder with all the bracing and the relative stiffness of the top lateral bracing will be represented in this stage. Construction stage 3 is subdivided in 4 stages, where the first stage is pouring of the concrete deck in section G11, G12, G13, which represent approximately the positive moment zone of the deck, of the bridge. Part 1 is where the deck is still not acting compositely with the girders, with the steel. So only when concrete load is activated. Second stage of the CS3 is that the deck stiffness is activated and the wet concrete load is deactivated. In the same way, construction stage 3, part 3, and part 4 regards the concrete deck parts over the negative moment zone. So GT1, GT2, which will be approximately as I said previously, 20% of the span length. Construction stage 4 is represented by the activation of the after composite loads, which are dead load of components and attachments, dead load of wearing surfaces utilities. Construction stage 5 it's only represented by the long-term effect of the bridge. So I want to outline that self-weight of concrete deck slab will be defined automatically in the program in both phases. Before composite, where the concrete deck is represented only by the wet concrete load and will have zero stiffness. In the after composite stage, the wet concrete load is deactivated and the self-weight and stiffness of the concrete deck is activated. The boundary conditions are such as that fixed supports at the bottom of the pier columns and abutment bearings will be used. For both intermediate supports and abutments will be used elastic bearings to represent the elastic links to represent the bearings. But before diving into the modeling with the wizard, I would like to discuss about some assumption I did for the model itself, especially about the bracing system and diaphragms. Since not every component of these systems have been modeled. Regarding the internal cross-frame bracing system, they have the function to control box girder distortion. Since our scope is a global analysis focused on the main girders, this bracing and the relative distortion control has been neglected. About the external K-frames, they have to control the relative twist of adjacent box girders. In this case, neglecting the presence of external bracing consists basically of giving to the girder to the end diaphragms the entire torques generated by the loads. So this is assumption in the safer side. Sometimes in the design also some kind of assumption is done when the top girders must be preliminary dimension. Only the diaphragms over the required at the supports in forms of I shape will be then modeled. This why everything is this is done, because the modeling of the bracing system and it's a time-consuming task, especially when the focus is just to design and check the main girders. And approximating the stiffness of the internal external bracing system can be complicated. What is not complicated instead is to approximate the stiffness of the top lateral bracing system, the one that connect the top flanges of the the interior girder. This system, it's in this case, we will not model, but cannot be the presence of this bracing system cannot be neglected, because the top lateral bracing system control the torsional flexibility during the erection and the construction of the girder before the composite stage. To simulate the stiffness of a closed box system with the top lateral bracing system, therefore, there is a theory which comes in our help. It's called the equivalent plate method, where from a torsional perspective, the lateral truss is viewed as a fictitious plate with a purpose of effectively close the open section. In the design practice, this fictitious plate represent the torsional properties of the box when the tab girder is closed. In doing so, we don't need to model the top flange lateral system, which is another time-consuming stuff during the modeling phase. There are several types of top lateral truss system, bracing system. We choose the Warren type, the one with the diagonal in alternating direction, where the thickness of the equivalent thickness of the top fictitious plate it's shown. The equation is shown here from the theory, which is easily to be found on the design handbook of steel bridges from AISC, American Institute of Steel Construction. So we can see here appears the area of the top flange and the area of the diagonal. The equivalent plate model and the input of the top fictitious plate, it's supported by Midas Civil. We will see later on when we will open the Midas Civil and the cross-section properties. And this is a big advantage of the wizard, using the wizard and not having to model the top lateral bracing system is a good big save of time. So let's go now into Midas and create our model. First thing to do is I already created all the section and material properties in a separate model, and this is something that I suggest usually to do. So before starting the wizard, the modeling, the model with the wizard, is better to have, is a good practice to have already prepared section and properties, material properties in a separate model in order to import it. So when we go in properties, material properties, import, we can decide to import properties from the already prepared file. And the same way we can import the section. We can save this. I will save it on my desktop. Let's dive into the section properties. The section 1, if you remember well, we need to create the section from the Composite tab. In the Composite tab, we can choose Steel tab type 1, as this is asymmetric sections. If you remember well, these were the dimension of the cross section. This is the dimension of the plate diaphragm. These were the dimension of the pier cap. So what I've created is the steel tab cross section with the 25 centimeter deck thickness, 10 centimeter haunch, all steel elements, offset. I change it to top center in order to have the offset line coincident with the application load points. Selection material. In this case, we can select the material of the concrete of the deck, the material of the steel, and the properties will be automatically calculated, the relative ratio of the Young modulus, concrete steel, and the same density. In the same way, in the section 2, which has a bottom flange and the bottom flange and top flange with different dimensions. The plate diaphragm I shape as I section user define. UKB. From UKB, this was essential to define just to read the area, because from the area it's possible to calculate the area of the diagonal. It's possible to calculate the top fictitious plate thickness, which according to the equation that I showed before, this equation, it is 2 millimeters equal to 2 millimeters for the section 1, and for the section 2 has been determined as 2.2 millimeters. This theoretically should give, according to the equivalent plate theory, should give the equivalent stiffness of the tab girder when it's closed. This is the dimension of the piece of the pier straight. This is the column. Sorry, I have deleted. (2.5 meter) column, user-defined solid round. And this is the tapered section. Once set up the section properties and material properties, we need to set up the time-dependent material properties. Can be done in this way. We can use this creep plus shrinkage. We can use the European code to define this time-dependent material. Characteristic compressive cylinder strength of the concrete edge of 28 for our deck is 35 kilopascal. Relative humidity of the ambient 70%. Notional size in this case I've calculated this 0.24. We will see that it's also automatically calculated in later on in the definition of the composite section. So we have created the time-dependent material of creep and stay shrinkage. We can create also the compressive strength of the concrete. We can say deck concrete. The same way we define as European mean compressive strength of the concrete deck. It's at the age of 28 days is 43,000 kilopascal, class N. After done this, we don't have to we must not forget to link this time-dependent material properties to the material. So in this case, the concrete creep shrinkage and compressive strength must be linked to the material of the deck, concrete C3545. And we save. At this stage, we are ready to start the wizard. So in the structure tab, under steel composite bridge, we can find that we can take advantage of 3 girder type: composite steel eye, steel box, a closed box, steel tap, which is our case. 3 span, 48, 64, 48 meter. Deck width 12 meter. Now the offset we leave 0 because we don't need to create eccentricity of the centroid of the deck. Radius 500 meter. We choose convex. Boundary we choose with the substructure and bearing type. We want to elastic link of both for abutments and pier cap. Unfortunately, pier cap is not possible to in the wizard to input the tapered shape together with the straight. So it's not possible to input this kind of shape for the pier cap. So we in this phase we will just input the section constant section, length 9 meter, material it's C37, pier support is fixed, column maybe section 6, height. Also in this case we will see what kind of tweaks we need to perform after because we will input the total height till the pier cap, which is 10.5 meters. Also about the elastic link stiffness. Now we want to, for the pier that they need to be infinitely stiff in the longitudinal direction. So in this case we will see kz is properly corrected, and one of the two pier will be the two bearing will fix the moment in the transversal direction. About the abutment, we don't want to have infinite stiffness in the longitudinal direction, as we want the movement to be free in the longitudinal direction of the bridge. So we will just define it like a very small stiffness, and in the vertical direction for elastic links must be in this case we will assume infinite stiffness as well. About the section, the thickness of the deck is 0.25, number of girders 2. We have to girder space 6 meters from the center of the bridge each other, so 3 meters from the offset line. The deck is concrete C3545, girders is correct, bracing as well correct. Transverse deck elements. Now with this wizard, basically we are creating a grill edge model where the deck is represented by dummy beams. This is the distance we want to. This is the spacing of these dummy beams that we want to. Is basically the discretization of the deck. In this case, I assume 2 meters. Bracing details. We will assume only over the support. What kind of bracing? We said that we want a single beam, which is plate diaphragm. We will assume a beam behavior, and we will modify this accordingly. The section of the girders, we have 3 divisions. We have section 1. It's not symmetric, so we will have section 1 from 0 to 38 meters, which is 80% of second span. After we have section 2 from from section G21 to section G22, included G12. In this case, we have from 38 to 160, which is the total minus 38 is 122 meters. From 122 to 160 meters length, section 1 again. We will copy current girder data to other girders as well. So girder 2. Stringer, we will not use any stringer. Generate 10 point elements. We don't need this because this is a requirement of ASHTO. So we will uncheck this. Going to the load. We said that we have edge barriers at the 50 centimeters both edges. The total. What's important in this section is in this tab that the summation of this lengths must give the total deck width. So in this case, B2, we have 5.5 meters, which is the left part of the carriageway, together with the shoulder, so lanes plus shoulder. B3 is 0. Before, again, 5.5. In this case, we will have 12 meters total. The dead loads. The dead loads of before the composite stage usually is given equally to all the girders, because it's assumed that for the the wet concrete load distribute equally beside the eccentricity on all the girders. We will assume self-weight before composite DC. Wet concrete weight density of 25 kilonewton per cubic meter, thickness 0.5, 25. We will neglect in this case the haunch for simplicity. The barrier, we will use barrier of 1.5 kilonewtons per meter. Median strip we don't have. Wearing surface, weight density we will assume 22 kilonewton per cubic meter, and thickness 0.10. These are the load acting after compositing. It's possible to define also in this wizard also the moving load case. In this case, we will use Eurocode, live loads, traffic lanes. We will define the three outmost traffic lanes in order to get the most critical effects on the outer girder. So 3 lanes. The lanes according to Eurocodes are 3 meters wide. So we will use the one, the axis of the first lane from the left is 2 meters, considering that the first half meter is occupied by the barrier. After we have a spacing of another lane at 5 meters, 8 meters, so 3 meter spacing, as we already know. Vehicles, we use load model 1 vehicle. In this case, we will leave everything like it is for adjustment factor because these are governed by the national annex. In this case, also for C factor for tandem system DL, we will leave the same. In this case, this is not the focus of our webinar. So, construction stage. In this case, we need to define, it's automatically defined that the D1, D3, and D5, which are the deck parts over the positive moment zone, act before, and D2 and D4, which are the deck parts over the negative moment zone, will act in a second stage. What we have to define in this case is the length. What we want to, so in this case, the length of the negative moment zone, left and right, we have 10 meters. For the support 1, and also 10 meters left, 10 meters right for the support 2. About the construction stage definition, in this case, is assumed, like I described before in the slides, that the deck over the positive moment zone is put before the deck in the negative moment zone in order to decrease as much as possible the cracks into the deck. So we will leave everything. About the duration, we will see we can change something later on. Reinforcement as well. It's possible to define the reinforcement in this wizard right now. We can define now or later on. It's better to define later, in my opinion, just before performing the design. Let's click OK. Let's take a look at the model. So we will see that the pier cap are not tapered, and we will see what kind tweaks and adjustments still need. So before proceeding with the analysis of the bridge, after having used the wizard, let's take a look at the wizard itself, the model itself created by the wizard. So we see that it seems properly made. The grillage model is being created through the group of the dummy beam elements. Dummy beam elements 2 also are created to connect the to create the load barrier load over the deck. We see that it's created automatically. It creates a new section called the girder width rectangle 8. It's a section of 1 millimeter by 1 millimeter, just with a very small stiffness. And also the material assigned to the dummy elements is called dummy material. We see that is has the same properties of the C3545, but it has just a weight density equal to 0, and this is automatically created by the wizard. So saving a lot of time in creating the grillage. Plate diaphragm are used only are created only over the supports. Section 1. We see that section 1, section 2 are properly assigned. What is for sure to be adjusted will be the pier cap, where needs to be created the tapering, and moreover also the height of the column, which is not 10.5 meter, it must be 7.5 meters. So 3 meter of the top of the column must be cut, and the top of the pier cap must be connected to the bottom of the pier cap through elastic link type rigid or a rigid link, depending whether we want to use master nodes and slave nodes or not. So the geometry has only this adjustment to be done. The elastic link seems correctly placed. They are also correctly placed also with the proper local direction as perpendicular to the bridge. We can open the elastic link properties in forms of table. We can modify the view, tile vertically the two, so we can go to check all the nodes of the elastic links, which kind of stiffness has been assigned, and we can change that manually. But this is very small and quick adjustment that can be done. Let's take a look at the most important part, which is the construction stage. So as you can see, the construction stage are already created, as we discussed. The duration has been assigned of every construction stage of 10 days. This can be modified. In this case, the 3.1 is the let's analyze all the stages. So in the construction stage 1, the substructure, the coping group is the pier cap basically, are created, are installed. Boundary condition, subtraction support. Subtraction support in the boundary condition are the fixed supports basically. We can go to select this and see that it is related to that. The stage 2, girder and bracing are activated. The duration is already 10 days. We can modify that boundary. Of course, girder elastic link, girder rigid link, which connect the top and the bottom of the girders are created. Girder elastic links are the bearings. The load, we don't have any load activated. In the stage 1, we had the load DC11. DC11 is the self-weight of the substructure, automatically assigned from the wizard, and this is static load case self-weight. We can see it's the one assigned as this DC11. Construction stage 2, 3.1. We can see that no elements is created. The boundary condition, no boundary. The load is DC1 part 2. DC1 part 2 is the wet concrete load of the first part of the deck pouring. We can take a look this under the wet concrete load. We can display this. We can display in the tables that this one is assigned to DC1 part, to the group DC1 to wet concrete load. So this is also properly assigned. In the construction stage 3.2, the damming beam are created with their stiffness, and the load, the wet concrete load, is deactivated. This is for the first stage of the pouring of the deck, so the parts over the positive moment zone. And the same thing, the same two stages are created for the pouring of the deck parts over the negative moment zone, so 3.3, 3.4. In this case, DC1, 3 is the group of the group load of the wet concrete load. Stage 4, DC2.1, this D1 are the dead load of the wiring utilities. D1, DC2 are the dead load of component attachments. So basically the loads after composite stage. In this case, no boundary. The boundary of the dummy beam 2 is created because the deck is this is the dummy beam 2, if you remember well, are the dummy beams at the edge of the deck, the longitudinal, just to assign the edge barriers load, as you can see. And this is where the barrier load is automatically applied. So the dummy beam 2, yeah, it's not for the from the mill load, it's just for the to connect all together the transverse deck beam, what is normally done in grill edge models. So what else? Let's take a look at the stage one by one, thanks to this. So stage 1, only abutments and fixed supports are created. Stage 2, the girder are installed with the bracing and the elastic link. Stage 3.1, let's take a look at the loads. The wet concrete load in the positive moment zone, first pouring stage. Stage 3.2, dummy beam, the wet concrete load disappear and the dummy beam with their stiffness create the composite section in these parts of the deck. Stage 3.3, the wet concrete load on the negative moment zone. Stage 3.4, deck stiffness acting. Stage 4, it's the barrier and where the post composite loads are applied. So in this case, we have the barrier and the wearing utilities, the wearing load acting. Construction stage 5, it's just for long-term 10,000 days, so for long-term effects. Of course, what the designer can do in this stage is to change the duration. For example, between the pouring of the concrete and the deck acting stiffness, as we can see that between the stage 3.1 to which is assigned 10 days of duration, and the stage 3.2 where the deck is the dummy beam, the deck stiffness are acting, is there are only 2 days of difference. In this case, we can adjust this to 20 days according to the concrete mix, to the mixed concrete which is chosen and the additives which are chosen. So this before doing the analysis of the bridge, basically we don't need to perform much. Everything is already modeled, and this actually honestly can save a lot of time in this phase. As I said, only the geometry of the pier cap, because there is a limitation in the wizard that the a tapering straight section cannot be assigned into the. So when we are ready for the analyze the model, just before that, we need to look at some option in the analysis control data. One of these is in the construction stage, because by default only direction load 1 is defined as a load cases for direction load. The direction loads are the load cases distinguished from dead load in the construction stage output. So basically, when we have to create load combination, it could appear on direction load 1. So the first thing is to add direction load 2, which must include wearing surface and utilities, because in direction load 1 by default is included only barrier and additional load. And of course, we want to have distinction between these two. Another option we need to be sure that is check on is the including dependent effect. and all the time dependent effect control data. So the number of iteration we want for the convergence creep, auto time step generation for large time gap. The auto time step are not will not be displayed into the outputs. It's just for our use to optimize the resources. And yes, so these are the main options in the construction stage analysis control data to be controlled. Of course, this I already checked up, and 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 the moving load, of course, the load of the moving load is not yet created. So in this case, we need to create a moving load. I have created a moving load LM1 called LM1, including the load model 1, vehicle load model 1, and the selected lanes to be applied are the 3 lanes as shown in the model in the wizard. Just want to show now the traffic lanes that I have created in the wizard. So layer 1, layer 2, layer 3. And of course the load combination. Load combination can be created after the analysis. So once we run the analysis, we can create some load combination. We can decide to either auto-generate those in the steel tab or concrete design tab. In this case, I have create auto-generate some load combination. As you can see, it's the auto generation load combination supports several codes. Eurocode 0, you can decide what kind of load factor you want to have for permanent pre-stress settlements, and also whether the road traffic you want to have characteristic value, frequent value, so you can create the traffic load group as well directly into the load combination here. I've just created 2 example load combination, one at ULS and one at the SLS, just to show some results. In this case, we can check the reaction forces, FZ, for LCB, CBS L1. These are the reaction forces, the supports. And let's take a look also some beam diagrams. In this case, we are focused on the only main girder, so we can decide to activate only main girders and take a look at some beam diagrams. So M1 bending moment, we can choose as value min max only. Torsion MX, share FZ. We can decide to show the diagram only for the part 1, which is the steel girder, or the part 2, which is the concrete deck. So it's very easy. The output is very clear. We can use also the moving tracer to track the position of the vehicle load, which maximize the force in the elements that is under object. In this case, for example, beam forces moment. We want to have the maximum bending moment. For example, of this key element. It will show the position, the application of the load. You can of the vehicle load. Actually, you can define the font of the load. About the design, we know that Midas is capable also of doing the design of the elements of the bridges. When we go in the tab design, we see that it's possible to do a composite, especially a steel design. In this case, can be done for the bracing, but for the girder, which are composite steel composite elements, is needed to perform composite design. As you can see, Eurocode is supported in both steel composite design. One thing to check at the beginning is that in the tools, preference, design load code, in steel and concrete tab, and also in the composite tab, Eurocodes must be selected because normally by default American code is selected. This is important. I will show why when defining the reinforcement in the cross section. Another tweak to be reminded is that to perform the design also the composite, the load combination must be created in the steel or either in the steel design tab or in the concrete design tab. In the composite steel girder design, no load combination are required. So going to design, having selected the Eurocodes, let's take a look to all these elements shown in this window. The design parameter are basically, this is very powerful. We can choose some national annex. In this case is shown on the France. This is the latest release of the Midas Civil. But all the parameters are according to the general Eurocode recommended by Eurocodes. Of course, they can be or the partial factor for resistance of materials and the strength whatsoever can be changed, can be adjusted. Also the design life of the bridge in here, the K parameter used for the stress limitation, and also what kind of ULS and SLS we want to perform. In this case, by default, all of them are checked. I will leave checked even if we will not dive into it for all of them. Design material, this is another important, it's not needed anymore with the latest version of Midas Civil to create a composite material. It's important to select from the material list the S355 and just to select the proper concrete material and reinforce. In this case, I already selected C3545 and class B for the grade of main rebar, but by default, the concrete and the reinforcement selection are not shown. So this needs to be done and click on modify. The composites, the longitudinal reinforcement. This is what I mentioned before. Since we don't take into consideration during the analysis of the stiffness of the reinforcement in the composite, we don't need to define before the analysis. We can define directly in the design stage. In this case, we can use this window with a guideline, for example, of 5 centimeter, where we will place the center of the rebars. Input method B is very powerful because we can define the starting point and the end point of our line and define the number. In this case, let's define 30 bars diameter. For section 1, we will define P16 bars. Part 2, we can have to click add. The same from the bottom reinforcement. I forgot to add H bar in the previous. We go here and we do H bar and we do modify. And we apply. The same section 2. Section 1. Guideline 5 centimeter. Input method B. The section 2 is the section created in the first stage, so the one in the center mid-span where we applied the cross section 2, so for positive moment zone. In this case, we don't need to define different bars than the section 1, so we can leave P16 at the bottom, at the top, like the section 1. We forgot to do apply. So This is shown. I want to show just the section 2.1. What I meant before. We go in group, sorry, in works section. Section 1 is automatically created by the wizard for the part of the girders which have the section cross section 2, but they are poured in the later stage than the stage for positive moment zone, where we have the section 2 as well here. So let's continue with the longitudinal reinforcement. In this case, we can choose to add phi20. The section 2.1, as we saw, we are over the negative moment zone, but it's up to designer. This must be also checked. H bar phi20 part 2 add. Same on the bottom. Add, apply, and close. So in this case, we have defined also longitudinal reinforcement in order to perform properly the ULS check and the SLS check of the composite beam. Define flange and whip. This actually it's needed when shell elements, plate elements are used, so it's not the case. Longitudinal stiffness. Longitudinal stiffness are in form of the we have not defined in this case longitudinal stiffness, so we will not design them, but important to know that is possible. Design position. Design position. We can select all the girder elements that we want to control, except for the nodes. We don't need to select any nodes. In this case, we don't want to design also the bracing, so it's just an example. We can choose I and J. Check position, and we do apply. In this case, and the position for design output basically are the position of the elements of which we want to show the output. We want to perform the report, so we can choose, for example, the elements over the interior supports here, and one element over in the mid span. We can apply and close. The share connector are the added share stud. We can define everything, the connectors, the number of connectors in the cross section, the tensile strength, the diameter, so the M, basically the overall height, center to center, and the spacing. In this case, we will omit this design, but it's perfectly can be done. So in order to perform the longitudinal shear check of the composite girders. Transverse stiffness as well is possible to define the type of transverse stiffness. And the transverse stiffness of the end support also must be defined when performing. This is especially important for a shear buckling check. This has law as well. It's related to lateral torsion buckling data. In this case, we will not check the torsional buckling as the model was not it's not suitable for that. This can be done in the stage. Fatigue as well, service load combination. We want to just take a look of some ULS check, especially what will be the output of the report. We can click on design, performing composite steel girder design. It's very quick as you can see. Once this is done, we can take a look at the design results, especially for the bending resistance. We can see that in the table regarding the bending resistance, the web classification, the top bottom flange classification as well is done. And assign the section, the classification, the class to the section in order to define whether it is plastic, bending moment, or because we know that there are 4 class of section according to Eurocodes. I don't want to dwell too much on this. This is not the main scope of the webinar. It's just to show the capability during the design. We know that the class 4, the local buckling will occur before the attainment of the yield stress. In this case, for class 4 section, an equivalent area of the element it's calculated to determine whether the elastic bending moment resistance is achieved or not. So in fact, the effective section for the buckling is calculated for every element. So we can take a look before to this table where we can see that where the class section is defined as 1, the resistance moment is the plastic one, and where is, in this case, the red one are shown. We can take a look, give views. Class section 4 is defined by the elastic bending moment. Let's take a look to the print results with the latest release of the Midas Civil. The printout results are not anymore shown in Excel, but directly in Word. So as you remember, I chose only 2 elements. You can see that the report is clean. All the parameter are shown. Moment capacity. It's in this case we have an utilization factor of 68%. As plastic resistance is cannot be attained because this is class section 4. Yeah. The class of the cross section in both cases for negative bending moment, the positive bending moment is calculated. For negative bending moment, the class 4 is obtained for the element 110, and the resistance moment it's calculated according to the elastic the effective section. So in this case, we have that moment elastic bending moment resistance. In positive, of course, this is the class section is still 4, and the elastic bending moment resistance is 7,000. Shear capacity. In this case, the plastic shear resistance is calculated, so it's compared with the shear buckling resistance, which is always, in most of the cases, less. So lateral torsion buckling also is performed, but let's say we will not focus on this, but the software also define this longitudinal shear or resistance longitudinal shear not having defined any shear studs is 0, so it's not good. It's called not good. Stress check reinforcement. The reinforcement, the limitation of 400 megapascal is fine. For the slab, the compressive concrete limitation is not achieved as well. So these are the one that the ULS SLS check that can be shown also in the report. SLS serviceability limits the SLS check we will not perform for longitudinal shear because we have not defined it yet. This is the J part of the element 110. We will see that it will be shown. The other element we selected is 118. The 118 is not good for, as we can see, the negative bending moment resistance is exceeded, sorry, and because the elastic bending moment resistance is 57,000 around 57,000, it's slightly exceeded of 1.3%. So yeah, this was everything for today. If you have any question, I know this webinar was a bit general, but because of time constraint, I couldn't analyze every aspect in depth. The main core of the webinar was to show the capabilities especially when modeling and post-processing and the design of the software, which are at very high level, as you can see.